Swayam Prabha. Digital India. Educated India.
I'll make this 5 volts. That is, what is the meaning of this is that it's the same as saying it is 5 volts in this direction. Okay. I've written this plus and minus inside the circle and say minus 5 volts. That really means it is 5 volts with bottom the plus sign and top is the minus sign. Okay. Now I'll introduce just one more complication. Okay. And that is that I will connect a resistance here which is 1 ohm. Okay. Now, first of all, for the voltage source, please let me know whether it is absorbing or delivering power. Okay. The question is, in this circuit, is the voltage source absorbing power or delivering power? Okay, I will broadcast the results now, and the majority opinion says that it is the voltage source is delivering power, and that is the correct answer. If you want, I will analyze it later and show you. Now let's make things a little more complicated. Okay. Now my question to you is, we already decided that the voltage source is delivering power. And how much is it? Okay. So now we have decided that the voltage source is delivering power, but of course we are doing engineering. That means that we have to be able to quantitatively calculate things. So now please mark how much power is it delivering. Okay, is it 5 watts or 10 watts or 7 watts or 3 watts? What is it? Sorry, the last choice is 35 watts, not 3 watts. Okay. So it is delivering power, but how much is it? Is it 5 watts, 10 watts, 7 watts, 35 watts? Or something else? Have I miscalculated everything? Okay, I'll wait for a couple of more responses before I close. Now, if you look at the results of the poll, maybe both B and D, that is 10 watts and 35 watts, have got more or less the same number of votes. And I can see more votes for 35 watts coming in. Of course, I mean, this is engineering, although this is fun. We don't decide things by vote. There is only one correct answer here. And let's calculate what it is. It appears that many of you have said 10 watts because the answer to the previous question, or there was some power of 10 watts in the previous question where we had only a voltage source and the current source. Remember, in this case, we also have an additional component, the resistor. So there is no reason that the answer should be exactly the same as before. Okay, it could be coincidentally the same, but you have to calculate it nonetheless. Okay. Now, first of all, basically to figure out how much power the voltage source is delivering, what we need to do is to find out the current through the voltage source. We already know the voltage across the voltage source, so all we need to do is to find the current through the voltage source. Okay. Now, this is a 1 ohm resistor and it's in parallel with the voltage source. So obviously, the voltage across this is 5 volts in this direction, or minus 5 volts with the opposite polarity. So what does it mean? That means that the current in the resistor would be 5 volt divided by 1 ohm equals 5 amperes. Okay. Now, you can clearly see that at this node we have 5 ampere through the resistor and 2 ampere through the current source, and the remaining branch to satisfy KCL must have 5 ampere plus 2 amperes equals 7 amperes. Okay. Now, as far as the voltage source is concerned, the voltage with this polarity is minus 5 volts and the current with that polarity following passive sign convention is 7 amperes. Okay. So V times I is 7 amperes times minus 5 volts, which is minus 35 watts. This minus tells you that it is delivering power, and this 35 watts is the amount of power that is delivered. So the correct answer is B. Okay. Now it's very easy to generate even more problems of this type. You can go on adding resistors and current sources and voltage sources and so on. Okay. And you can get some practice yourself. Of course, if you go to a basic book like Hayden Kimmerly, there are a number of problems, but even you can generate these problems yourselves. Okay. The only thing I would say is be very systematic and simply calculate V times I. Okay, based on the Kirchhoff's current law, Kirchhoff's voltage law, and so on. And for each element, do that properly, and you will get the right answer. Okay. So, in this itself, you can take as an additional exercise amount of power delivered or absorbed by the current source, okay, or absorbed by the resistor. Okay, you can calculate these things for yourself and maybe discuss it on the forum or whatever is convenient for you. Okay. Now I hope it's very clear that a resistor always absorbs power. A voltage source or a current source can absorb power or can deliver power depending on the circuit they are connected in. Okay. Now let me ask you another question. I have a circuit with a single voltage source and a number of resistors. Okay, I have only one voltage source and a number of resistors. Now, can the voltage source be absorbing power? Is that possible? I'm talking about a circuit with a single voltage source and number of resistors. Okay. We know in general the voltage source could be either absorbing or delivering power. Now in this case, can the voltage source be absorbing power? If so, why? Or if not, why not? Clearly, I think all of you guessed it correctly. If you have a single voltage source and all resistors, it has to deliver power. Okay. You cannot have all the elements in a circuit absorbing power. Then the question is, where is the power coming from? Okay. So you have to have at least one source in the circuit which is delivering power. Now, depending on the circuit, it could be more than one source, but whatever circuit you have, at least one of the independent sources that you have must be delivering power. Okay. So that part is correct. Now, having discussed voltage sources, current sources and resistors, let's move on to what happens in inductors and capacitors. Okay. Okay. Again, we know the IV relationship for the capacitor. The capacitor current is C times dV by dt. Okay. And the instantaneous power V is V times I, which is V times C dV by dt. Okay. Now, this itself looks a little complicated, and we can't tell whether it is absorbing power at some instant or delivering power. Okay, either is possible. Depending on if V and dV by dt are both positive, it's absorbing power. Similarly, if V and dV by dt are both negative, it is absorbing power. Or if V and dV by dt have opposite signs, it is delivering power. Okay, so all of these things are possible. Now it is more interesting to look at a slightly different quantity. Okay, let me rearrange this first. This is C times V times dV by dt. Now from basic calculus, you know that if you try to differentiate V square, what you will get is 2V times dV by dt. Okay, time derivative of V square is 2V times V dV by dt, and we have something like that over here. Okay, so we have V times dV by dt. Basically, so what we have is C times half of dV by dt of V square. Okay, I'll say C by 2 dV by dt of V square. Okay. So the instantaneous power that is going into a capacitor turns out to be directly proportional to the time derivative of V square. Okay. And this itself can be either positive or negative. Right. Now, a related quantity to power is what is known as energy. Okay. And what is energy? Energy is nothing but the integral of power over time. Okay. So let's say you take a definite integral from t1 to t2 and you have some element with V across it and I through it. We know that power itself is V times I. Okay, so the energy E that is absorbed by the element energy E absorbed by the element is given by the integral of Vi dt. And when I put some limits here, T1 to T2, okay, this means that energy E absorbed by the element over a time from T1 to T2. Okay, so that is what is meant here. So energy E, and depending on how long you wait, different amounts of energy will be absorbed. Okay, it's an integral quantity. So you have to specify the time over which the energy is absorbed, and that is equal to the integral of V times I dt. Okay. Now with this definition, we can look at what happens in a capacitor. Right? We saw that this power is C by 2 d by dt of V square. Let me write the capacitor again, Vi, and this is the capacitor C, and the power, which is V times I, can be written as C times V times dV by dt, which is C by 2 time derivative of V square. Okay. Now let me integrate this. Okay, and I'll also choose T1 to be 0, and I'll assume that the capacitor has 0 volts across it. Okay, this is just the starting point. I start from a capacitor that has 0 volts, and then V and I are varied in some way. Okay, they are related by I equals C dV by dt. Maybe I vary V or I vary I, it doesn't matter, but they vary in some way. Okay, and finally I reach a certain time T2. Okay, so the energy absorbed by the capacitor from T1 to T2 is nothing but integral of C by 2 d by dt V square dt from T1 to T2. Okay, and let's say that at time T2 capacitor has certain Vc volts across it. Okay, now you can see that this time derivative operator and the integral cancel each other, and you will be left with C by 2 times V square with the value of voltage at T1 to value of voltage at T2. Okay, and this is given by C by 2 Vc square. So what this means is that a capacitor, if you charge it up to a voltage Vc, will have energy. It has absorbed all this energy, right? So it will have an energy C by 2 times Vc square across it. Okay? And also, just like the power in a resistor was always positive, the energy in the capacitor is always positive. Vc itself could be either positive or negative, but the capacitor would have stored some energy. Okay? Is this clear? Any questions about this part of it? What I did was try to find out what the power dissipated in a capacitor was, and it comes out as some, not power dissipated, power absorbed by the capacitor is, and it comes out as some derivative of something. Now energy, which is the integral of the power, comes out to be half C Vc square. Okay, half of capacitance times the square of the voltage, and that is always positive. So if you charge a capacitor from its discharge state from 0 volts to a voltage Vc, it would have absorbed an energy, or it stores an energy of half C Vc square. Okay. Any questions about this? How we derived it, or any sticky points? So now I also started from T1 equal to 0, where capacitor has 0 volts across it, and nothing is stored in it. Okay, no charge, no fields, no energy. And I took it all the way to voltage Vc, and it has an energy C by 2 Vc square stored across it. Okay, so from this we can say that now the important thing is I didn't worry about how exactly the voltage changed. Okay, it went from 0 to Vc in whatever manner. But finally, the energy stored in the capacitor is half CV square. Okay. So the energy in the capacitor is not dependent on how you reach that voltage, but it's dependent only on the voltage across the capacitor. Okay. Okay. Now it doesn't matter what is meant is, let's say I plot the voltage across the capacitor V as a function of time t, and let's say this is the voltage Vc. Okay. Now I could have reached it as a straight line. I could have reached it in some strange way like this. Okay. Or I could do even wilder stuff and go there. So as long as initially it is at 0, so that means its energy, everything is 0. And finally I reach a voltage of Vc. So that means that once I reach here, I would have totally absorbed an energy of half CVc square, and that is stored in the capacitor. Okay. Now there is a question on what happens when you discharge a capacitor. Okay, so let's say again, so I had called this time as T1, and I'll call this T2 where it is at Vc, and let's say it goes to 0 from here. Okay, and I'll show some arbitrary waveform. It will go to 0 at a time T3. Okay, so now if you look at what is happening during this time, integral from T2 to T3, C by 2, integral of those whole thing. Okay, this is the energy absorbed by the capacitor during this time. Okay, now what do we get? Again, the integral and the time derivative cancel each other, and we'll end up with C by 2 V square with the voltage at T2 and the voltage at T3. Okay. Now what is this going to be? This will be C by 2, and voltage at T3 is 0 because it reaches 0 volts, minus voltage at T2 is Vc. Okay, so we get minus half CVc squared. Okay, what it meant is it is negative, so that means that the capacitor gave out energy. Okay, so if it is positive, the capacitor absorbed energy, and if it is negative, the capacitor delivered energy. Okay, so if you charge the capacitor to Vc, it would have stored an energy of half Cv square, and then now if you discharge it back to 0, it gives back that energy. Okay, so a capacitor does not dissipate energy, whereas in a resistor, the energy you put into it, you cannot get it back, whereas a capacitor, you charge it to some voltage, it draws some energy from the source. Okay, and then you discharge it back to 0, it gives back all the energy to the source. Okay, so a capacitor does not dissipate any energy, but it can store energy. I hope that is clear. Okay. So that means that the energy stored in a capacitor can be recovered. Okay, you can use that, and it's one of the important uses of a capacitor. You store energy in it, and then you can also get the stored energy. Okay. Now let's take the example of an inductor. It's very similar to that of the capacitor. V and I. Okay. Now we know that the voltage is proportional to the time derivative of the current. So the power is V times I, which is L times I times di by dt, and this itself can be either positive or negative, and we use the usual algebraic trick to write this as L by 2 d by dt of I square. Okay, and again this itself is not an interesting quantity, as the energy absorbed by the inductor equals, and for a duration t1 to t2, equals the integral from t1 to t2 of L by 2 d by dt of I square with respect to time. So again this will be half L and I square. This will be the value of I at t1 and the value of I at t2. Okay. So if you start from an inductor that has zero current in it and go to a current IL, okay,